It's a biological fact, but people have been arguing now for a century what accounts for this 3/4.
In the decades following Kleiber's observation, the mystery only deepened. Researchers discovered that brain size also roughly scales as mass to the 3/4, and so does an animal's growth rate and the amount of blood pumped per minute. But not every property scales as mass to the 3/4.
If you ask how long a creature will live, a mammal, that tends to be proportional to its mass to the 1/4 power. 1/4, not 3/4.
So that means if you double the mass of a mammal, then on average, its lifespan is around 19% longer. Similarly, blood circulation time also scales as roughly mass to the 1/4, while breathing rate and heart rate both scale to the negative 1/4. They're not all 3/4 power laws, but they are all multiples of a quarter. So the question on everyone's mind was, where are these quarter power scaling laws coming from?
At the time, Jim was associated with the Santa Fe Institute. And he started asking around, is there anyone up here that's interested in these biological scaling relationships? And then the president at the time said, you know what, I know of this physicist who's up at Los Alamos who was talking about biological scaling relationships. And so we met Jeffrey, and it was like immediately, it's like we'd been talking about the same things for like years. It's like, finding, someone who's been like speaking your language, but no one could understand you.
So West, Brown, and Enquist teamed up to try and find a compelling explanation for Kleiber's law.
They started by assuming 3 simple premises. The first premise is that the networks that distribute resources are space-filling, since they need to reach every cell in the body. The second premise is that the terminal units of those networks, the thinnest segments on the outer periphery of the delivery system, have the same width regardless of the size of the organism. That is, the outermost blood vessels that carry nutrients to an elephant's skin cells are about as thick as the ones in a mouse. The elephant just has many more of them. And the third premise is that over time, evolution has driven these transport networks toward an efficient design.